So here we have a very interesting problem right here. So let's suppose that we have let's say a charged particle. Let's say that it has a charge Q, and we're gonna say that it has an initial position at r is equivalent to 0. All right. Let us suppose that it is moving initially in. Let me just label my axes just for a moment. There you go. Let us suppose that it is moving initially in the x hat direction, so that we have a initial velocity of v naught is just equivalent to v naught x and then x hat. And then and then in this scenario, what we're going to have is we're going to have an electric field exerted, a uniform electric field exerted across the y hat direction. And then on the z hat direction, we have a uniform magnetic field. So let me just label this right here and label this right here. So now the problem is to find an equation of motion. Well, at least for the sake of time, we're going to find the velocity as a function of time of the particle given these initial conditions. So the first thing that we're going to do is we're going to write the Lorentz equation for this scenario. So what I'm going to do, I'm going to assume that you have the initial picture over here, but I'm going to redraw it just for more drawing space. So what we're also given that the electric field is just equivalent to the magnitude of the electric field in the y hat direction, and that the magnetic field is just equivalent to the magnetic field in the z hat direction. The first equation that we are going to use is obviously Newton's second law, and we're going to ignore the effects of gravity here since we're dealing with particles at almost the microscopic scale, so almost like a proton or an electron or any fundamental particle with a set charge. So the net force is equivalent to, obviously we're going to use the mass times acceleration, but I'm going to write the acceleration as the time derivative of the velocity as a function of time, obviously. So, and this is going to be equivalent to Q, or basically the Lorentz force, plus V cross B. Now, earlier with how I drew my axes, you're going to guess that I am going to be using Cartesian coordinates for the setup of this problem. So at first, we're going to evaluate the Lorentz force and divide it into components. So obviously, the first thing that we're going to do is we're going to evaluate the cross product of the velocity times the magnetic field, which is really just easy because, as you can see, we only have a magnetic field moving in the z hat direction. So V cross B is equivalent to, we're going to be using just the determinant definition, y hat, z hat, and then Vx, Vy, and then Vz. Like I said, divided into components, and then we have magnetic field being 0 in every component except the z hat direction. Now, upon inspection, you're going to see that this is going to evaluate as x hat times the velocity at y times the magnetic field, and then plus y hat times, this is going to be negative the velocity in the x direction times the magnetic field. And then obviously in the z hat, the determinant has 2 zeros in the second row, so it's going to have a 0 determinant over there. So we have evaluated our cross products, so this is going to be equivalent to, I'm going to write it as Vy B x hat, and then minus Vx B y hat. All right, so let me just erase this for a moment right here, and then And now what we're going to do is I'm going to redraw this slightly more. So we have right. So now that we have found the cross product of the velocity vector and the magnetic field, what we're going to do is now we're actually going to split this vector equation into its components. So what I'm going to be writing is, I'm going to, instead of using Leibniz notation, I'm just going to use dot notation for labeling my velocity derivative. So in the x hat direction, I'm going to have the mass times Vx dot, which is going to be equivalent to, obviously there's going to be nothing in the any contributions from the electric field in the x hat direction because the electric field is going in the y hat direction. So now what we're going to do is we're going to write instead the x hat component of the magnetic field. So this is going to be equivalent to Vy times B, and then obviously we're going to multiply it by the charge. And then after that, we're going to be writing the y component of this. So we have the mass times the velocity in the y hat direction, or its time derivative. This is actually going to be equivalent to, this is going to be Q times the electric field, because like we said, and then this is going to be minus velocity, actually Q, and then B times the velocity in the x hat direction. Now, I'll leave it to you to wonder that there's going to be nothing in the z hat direction. And so if you solve the differential equation and ignore the other components except from the z hat direction, what you're only going to get is another constant velocity equation. So these are the two main equations that we are primarily concerned about. What I'm going to be doing is I'm going to be dividing both sides by the mass, and so that I get the velocity in the x hat direction is just going to be bq over m, and then this is going to be qe over m q. All right, and then I'm going to define new quantities just for the sake of writing less. I'm going to define omega naught as equivalent to the charge times the magnetic field divided by the mass, and I'm going to write omega equivalent to the charge times the electric field divided by the mass. So rewriting this equation, what we're going to get is, so this is going to be omega Vy, omega naught Vy, and then this is going to be omega 1 minus omega naught. All right. So we can really solve this system of differential equations in many ways. The technique that I'm going to be using for solving this differential equation is using the method of Laplace transform. So first of all, let me just rewrite this, because we don't have to worry about it. And then I'm gonna rewrite my components. So Q B over M. So we have Vx naught equivalent to right. So the first thing that we're gonna do, like I said, we're gonna be using the method of Laplace transforms, is we're just gonna take just straight out a Laplace transform. So obviously, if we take the Laplace transform of a time derivative, what we're going to get is we're going to use S as our domain for taking the Laplace transform of any function. So this is going to be s times v tilde. I'm going to be using tilde for the Laplace transformed version of a specific function or a variable. So s times vx and then minus, and then minus, this is going to be the initial condition, so this is going to be vx naught, which is going to be equivalent to a Laplace transform of a constant times a variable. That's going to be omega naught times vy tilde. And then for the second one, what we're going to get is similarly the same thing. So you get svy tilde. And then we said that the initial condition of the particle is that it wasn't moving in the y direction. So the vy naught is going to be 0. So what we're going to get is the Laplace transform of just a constant is just going to be that constant divided by s. So omega 1 divided by s. And then minus omega naught times x hat or x tilde. Right? Alright, so now that we have the equations in place, what we're going to do is we are actually going to rearrange them a little bit just so that we can get a nicer representation in matrix form. So what I'm going to be writing is, I'm going to move this to the other side, so vx naught, then I'm going to move the vx naught over here, so we have svy tilde. It's going to be equivalent to this. So here we have our matrix equation, or I guess I should make it more clearer. This is going to be written in s negative omega naught, then omega naught, and then s times vx tilde, vy tilde. It's equivalent to so here we have our matrix equation, and really what we can do is just use Kramer's rule to find the solutions for each component of the velocity. So I'm going to be erasing the chart because I assumed you get a initial scenario of what is happening. So we have those conditions out. Right. I'm currently moving in the process, so there's a bunch of junk that is preventing me from just moving slightly closer to the board, but don't mind. So what we're going to be getting is that obviously the first thing that we're going to do is we're going to evaluate the determinant. So this determinant is actually going to turn out into s squared plus omega naught squared, which is never going to be 0 because it's a squared, assuming that the only inputs are real valued variables, which for s is a real value variable greater than 0. So with that out of the way, when I'm going to evaluate vx tilde is equivalent to the determinant with vx naught and then omega 1 over s times negative omega naught and then s divided by s squared plus omega naught squared, which is going to be equivalent to vx naught s and then plus omega 1 omega naught over s all divided by s squared plus omega naught squared. What we're going to be doing is that we're going to be splitting up this fraction so that we can identify any noticeable inverse Laplace transforms, and we're going to be rewriting this as, so this is v x naught times s divided by s squared plus omega naught squared. I can delete that part. And then this is going to be plus omega 1 over s times omega naught s squared plus omega naught squared. So you can already see that this is going to be the inverse Laplace transform for cosine omega naught t. And then what you can see here is that you have a product of two Laplace transforms. So we're gonna have to use a convolution in order to evaluate this, or a convolution theorem. Yes. So obviously, the first thing that we're gonna do is that now that we have our expression over here, what we're gonna do is take the inverse Laplace transform. So obviously, taking the inverse Laplace transform on the first term, this is gonna lead us to Vx naught cosine omega naught t. And then for the second one, I wish I had a larger whiteboard or better a chalkboard. So as you may recall from your differential equations course, the inverse Laplace transform of two functions, so f and g, is just equivalent to the convolution of f and g. And if you don't remember, the convolution between two functions was just equivalent to an integral from 0 to t of f of t minus v and then g of v dv. So the first thing that we're going to do is we're going to evaluate f of t. We're going to say that f tilde is omega 1 over s, so that's so that f is just going to be omega 1. So, and then g of v, this is going to be sine of omega naught t. So this is going to be omega 1 sine of omega naught t dv. And then obviously change the variables. So now what we're going to do is we're going to evaluate this integral in order to obtain that so don't mind me just I really have no space. So this is going to be omega 1 times, this is going to be a sine, so it's going to be negative omega 1 cosine over omega naught evaluated over t and then 0, which is I'm going to reverse the signs here, so 1 minus so really we already found our expression, and so what we have is I'm going to write it down on the bottom just to save more marker space, or even with that, let me use a smaller marker if I can find it. Vx is equivalent to then plus Now, what we're going to be doing is now that we're going to evaluate the y component of this. So I leave it to the reader to simplify this down. So now that we have that, what we're gonna do is evaluate the y component of this. So again, using Kramer's rule, we're gonna see that the y component of this is, I'm instead gonna be actually using I'll use the smaller marker. So we get that Vy tilde is just equivalent to obviously 1 over s squared plus omega naught squared times the determinant of s and then omega naught and then Vx naught and then omega 1 over s, which is going to be equivalent to omega 1 minus omega naught Vx naught over squared plus omega naught squared. As you can obviously see, what we're going to be doing, or you can predict what I'm going to do next, I'm going to split this fraction up in order to get omega 1 and then times s squared plus omega naught squared. I'm going to put in omega naught here and then divide both sides. Then minus Vx naught and then times omega naught times s squared plus omega naught squared. So really we have two similar Laplace transforms. So what we're going to be doing is I'm going to be simplifying this down. So omega 1 over omega naught minus Vx naught times the Laplace transform of, this is going to be sine of omega naught t. Right, and then now we can just easily evaluate the inverse Laplace transform in order to get that Vy is equivalent to omega 1 over omega naught minus Vx naught times sine of omega naught t. So there you have it. This is a derivation of the velocity as a function of time for a particle, a charged particle in a crossed electric and magnetic field. So I'm gonna write this in components, in a component notation, yeah. So this is going to be the velocity as a function of time. It's going to be equivalent to, this is going to be Vx naught cosine omega naught t omega naught t plus, actually, I'm going to simplify this down actually. Vx naught cosine, then plus omega 1 naught. What's it cosine? Times 1 cosine omega naught t, then plus omega 1 over omega naught So then this is going to be in the x hat direction plus y hat. This is omega naught minus v at naught times cosine, well no, yeah, it was sine omega naught t. So there is your function. I'm going to leave it to the reader as a simple exercise to integrate the velocity equation with the initial conditions that the initial position was at just the origin point. So 0 x hat plus 0 y hat plus 0 z hat, and then you can derive it to get the position. You can simply note that if v x naught was equivalent to omega 1 over omega naught, and if omega 1, we're gonna simplify omega 1, omega naught to be, this is gonna be E over B. So this is going to be what we call the drift velocity, in which if you set your component to be equivalent to that, what you're going to be getting is that you're going to be getting a constant velocity in this direction. This is actually omega 1. So there's also an interesting aspect of this, of the results of this differential equation. The curve of this is going to be more like a growing circle. So if I'm going to be drawing it with, this is x hat, this is y hat, and then it's going to be growing like this. So this is your what your curve looks like if you integrate it to find the position. If you have a non-zero z component, it's going to be looking like a cone, more like a cone with a curve tracing out the cone, kind of. So yeah, love solving this problem. That will be it.